Hello, my name is Nicholas Kinsella, and today I'm going to be presenting my work on estimating the Lahar hazard at Mount St. Helens. So where is Mount St. Helens and what happened? So Mount St. Helens is located in the Cascade Mountains of North America, approximately 150 kilometers south of Seattle. Mount St. Helens is the most active volcano in that range, and the current active period began 3,900 years ago. There are 40 known historical eruptions in that period, and on the 17th of May 1980, a very significant eruption occurred where a magnitude 5.1 earthquake caused the total collapse of the north side of the mountain, which was the largest subaerial landslide in recorded history. This then allowed the sudden escape of pressurized material from inside the volcano, destroying the summit in a massive explosion and creating a horseshoe crater. The Gary Rosenquist sequence of images on the right show this nicely. Um, so glaciers don't normally develop at this altitude or latitude. However, the crater rim has provided shade and crater debris have provided insulation, so much so that actually a glacier has developed in this area. By 2001, the glacier was about 200 meters thick at its thickest, with a 100-meter average, and had a volume of 120 million meters cubed. A resurgent lava dome split the glacier between 2004 and 2008. And this is important because the rapid melting of glaciers due to volcanic action are actually Lahar hazards. And Lahars are a mud-like mix of pyroclastic material and water. And the classic example of this is the tragedy of Armero in Colombia, where a lahar from the volcano of Navarro de Ruiz destroyed the town, claiming the lives of some 22,000 people. Um, in the past, St. Helens Lahars have actually traveled between 50 and 100 kilometers away from the volcano. And although the area is relatively sparsely populated, roughly 750,000 people visit Mount St. Helens annually. And so this hazard can't be underestimated. So this study will use multi-temporal digital elevation model analysis to measure the volume of Lahar features and attempt to contribute to an understanding of the potential of this hazard in the area. Factors that were analyzed in the study include the mountain mass loss and the subsequent crater depth, and this is useful for estimating the maximum potential of that crater glacier growth in the future. The crater glacier thickness, and also its volume, to estimate how much water is up there, and the resurgent dome size, which hopefully will indicate volcanicity, the extent of volcanicity, and the seasonal snowpack on summit flanks. Obviously, if it's seasonal, it's not there in the summer, but if an eruption happens in the winter, then there's all the more water to contribute to a Lahar hazard. So data and methods. The study was conducted using a series of digital elevation models and comparing those models to each other. Two of the digital elevation models were produced using orthophotos from aerial photographs, that for 1979 and 1984, and a program called MicMac, where if you take a photograph of an area from multiple different angles, you can compare control points to each other's relative position. And from that, using a bit of computer trickery, you can not only determine the X and the Y dimensions, but you can also determine the Z dimension, so the altitude. From that, figure 5 was produced, which is a digital elevation model. The green circle indicates an area where there's a bit of cloud cover, but we're going to talk about that in a minute. The third digital elevation model from 2008 was from the ALOS program of satellites. And although it says 2008, it's actually from between 2006 and 2011, and its actual date is not entirely known. Digital elevation difference rasters were generated by subtracting in ArcGIS Pro's raster calculator one digital elevation model from another. So, and two were created. So there's a digital raster from 1979 to 1984, and another one from 1984 to 2008. To check to see the accuracy of these digital elevation models, the two accuracy analyses were undertaken. The first was the root mean square difference one, and the second was the normalized median absolute deviation. These do similar jobs, but the difference is the root mean square difference considers all data points even outliers, even low figures, high figures, and noise. Whereas normalized median absolute deviation only considers data points that are within one standard deviation of the mean of the data set. Um, in both of these cases, we're looking for low numbers. So the lower the number, the lower the estimated change in the area. And the study site shown in figure 6 in zone 2 was chosen as an area where it is very, very likely that no elevation change has taken place in that area over the entire course of the study. So from 1979 to 1984, the RMSD and MNAD were seen to be 3.28 meters and 2.79 meters, very, very close to zero. And also in 1984 to 2008, they were 8.02 and 3.51. Now, although those are a little bit higher, this region is farmed for things like Douglas fir, which is a pine tree native to this part of the world. That tree can reach heights of 45 meters. So these figures are well within the normal limits of things like vegetation growth. So the data sets are nice and accurate. Now, to deal with those cloud gaps in the data, kriging was used to fill those gaps, and the Krieg models in figure 7 for the 1979 to 84 raster are shown, as well as the Krieg model used for the 1984 to 2008 raster. These created the two digital elevation change rasters you see in figure 10. The one on the left shows the very large material lost in the red section in the center of in the picture. At the top, you see the blue, which indicates accumulation. And the accumulation is obviously pyroclastic material falling down the side of the mountain and eventually coming to a rest there. In figure 10 on the right-hand side, you have the blue area in the middle, which is an indication of height growth. That is a combination of the resurgent dome and also the crater glacier. Also, you can see the blue, the light blue of the snowpack around the summit. And then after this information was collected, these were digitized, as you see on figure 11, where you've got the outline of the crater in yellow, the glacier outlined there as well, the resurgent dome and the snowpack. And this is what was used as the basis for the analysis. So the 1979-84 changes. The total material lost from the volcanic explosion was 2.615 kilometers cubed, a truly enormous figure. The USGS figure actually places this slightly higher at 2.829 kilometers cubed, and that's about 100%, 108% of the study figure. I'm not entirely sure where this, how old this figure is. It might be from the 1980s, before they had the kind of technology we have nowadays, but the difference is notable. This left a crater of 1.875 kilometers cubed in volume, which is again useful for understanding how much the glacier can grow in the future. The 1984-2008 changes, the dome growth, which occurred between 2004 and 2008, grew nearly 370 meters in height, and it extruded roughly 120 million meters cubed of volcanic material. Published information estimates this figure to be around 93 million meters cubed, which is 77% of our study figure. Glacier growth, the maximum height was recorded was 241 meters. The mean height was 84.6 meters, and the volume shown was 100 million meters cubed of glacier. Again, 2/3 of that being glacier ice, and 1/3 of it being debris and other material from the volcano, as stated in the published material. Published information puts the maximum thickness of ice at between 140 and 160 meters in 2003, indicating that maybe there's some growth going on here in the glacier and it's not simply a static phenomena. But without mass balance information, it's difficult to know exactly how much ice is there. But this could be done in a different study in a future date. The snowpack depth. The snowpack depth was a maximum of 45 meters and had an average depth of 18 meters. It's a seasonal phenomena. And the snowpack actually had around about 120 million meters cubed worth of material, which actually is slightly more than the glacier, which indicates that during the winter, if there were an eruption, that potentially doubles the Lahar potential, depending what time of year an eruption actually happens. So discussion. So study deficiencies. So the 1979 and 1985 DEMs were based on orthophotos, and obviously they had problems with things like cloud cover. This is not a major problem, but in cloudy parts of the world, this might not be as suitable as it was here. The satellite-derived DEM was taken over 2006 to 2011, as I said, and I thought this was initially going to be a big problem, but upon review of the literature, the dome growth and the glacier dome interface, which shifted quite a lot in 2004 and 2005, had largely finished by 2006. And so over the time that the DEM was actually taken, this is probably no longer going to be moving around as much, meaning that the data is probably quite good. Nevertheless, orthophotos are probably better overall for this kind of analysis. With regards to the findings, the thickest glacier, the glacier's thickness was measured to be greatest closest to the south and east of the crater rim, and the thickest ice was piled up against the resurgent dome. The lava dome growth largely occurred in the southern portion. The northernmost section is actually a remnant from the 1980-84 eruption, but that also showed about 20 meters, well, less than 20 meters worth of growth, but still measurable growth. The seasonal snowpack was a slight similar volume to the glacier, although a lot less dense. Future work. Yearly DEM differencing should be done to see if the glacier is actually growing or increasing. This will allow us to work out exactly the volume over multiple years and actually make a proper assessment on if it actually is growing or if it's shrinking. Published sources indicate that it is growing, but I need to see more information about that. So references are here, and I hope you found that interesting, and thank you very much for watching.